All right, so our first problem today is going to be example 1. So example 1. This is going to be from the uniform circular motion chapter. So example 1 says that a computer is reading data. A computer is reading data from a rotating CD-ROM. From a rotating CD-ROM. So at a point that is 0.03 meters from the center of the disk, 0.03 meters, right, or 3 centimeters from the center of the disk, from the center of the disk, the centripetal acceleration is 120 meters per second squared. The centripetal acceleration is 120 meters per second squared. What is the centripetal acceleration? What is the centripetal acceleration at a point that is 0.05 meters or 5 centimeters from the center of the disk. So from the center of the disk. All right, so to begin with, we know that our centripetal acceleration, AC, is given by the velocity squared of our object, or the magnitude of the velocity squared, divided by the radius away from our center of rotation. But we also know that the velocity of a point that's undergoing uniform circular motion is given by 2 pi r, where r is the distance from the center of rotation, divided by the period of that rotation. So how long it takes for that object to go around once. So if we take this velocity and we plug it in here, we're going to get our centripetal acceleration in terms of both r and the period. So right up top we have v squared, but v is 2 pi r over t. We're going to square that. We're going to divide by r. So up top we have 4 pi squared times r squared divided by t squared. And we're dividing all of this by r. So this is going to be equal to 4 pi squared, 4 times pi squared times r, all divided by the period squared. So now let's look at the different centripetal accelerations, right, for when we're 3 centimeters away from the center of this disk versus when we're 5 centimeters away from the center of the disk. So I'm going to say that our first centripetal acceleration, I'm just going to call it A1, is the centripetal acceleration when our radius is 0.03 meters, and A2 is the centripetal acceleration of a point on the disk that is 5 centimeters away from the center of the disk, right? So if we take the ratio of A2 divided by A1, right? So we have A2, the centripetal acceleration of a point that's 5 centimeters away from the center of rotation, divided by A1, which is the centripetal acceleration when we're only 3 centimeters away from the center of rotation, right? We can plug in the different values we get, right? Because we have an expression here for the different centripetal accelerations. So let's just punch those in. So up top, we have A2. That's going to be 4 pi squared times R2 divided by T1 squared. And all that is going to be divided by, excuse me, this should be 2. Right, and all that's divided by 4 pi squared times R1, all divided by T1 squared. So here we are dividing two fractions by one another. If you guys remember the very first lecture that we had, we know how to actually do this. So we take the top fraction and we leave it alone. So it's going to be 4 pi squared times R2. We're going to divide that by T2 squared, right? So we leave the numerator alone. And what we do is we take the denominator, we're going to flip it and then multiply it by the numerator. So all this becomes, this first bit here multiplied by T1 squared, right? Now we're flipping the denominator. T1 squared times 4 pi squared times R1, right? So in this case, the 4's cancel out, the pi squareds cancel out, and the times squared cancel out. You might think, well, that's a little bit weird, but notice this. So if we have a spinning object, right? Let's say that this is the center of rotation for our object. If we draw a radial line like this, right? If we have a point here, let's say that's 3 centimeters away from the center, and then we have a point here, which is 5 centimeters away, I want you guys to notice that even as this thing goes around, right, both these points are going to be rotating at the same, or with the same period, right? So basically, as this thing rotates, maybe I can actually do this. So as they rotate, they're both going to rotate together. And I know this is not the clearest example, but what I'm trying to get is the period for both of these things is going to be the same in this case. They're both moving at different speeds, right? Because they're both, or like they're each, a different distance away from the center. So they're moving with a different velocity, and they're in general going to have different centripetal accelerations. But since they're both part of the same rotating object, they're both going to cross the finish line at the same time, so to speak. So it's going to take the same amount of time for them to rotate back to their starting position, which is why T1 is going to be equal to T2. So this just leaves us, right? So we have A2 divided by A1 is going to be equal to, in this case, we have R2 divided by R1, R2 divided by R1, right? And now if we multiply both sides by our first centripetal acceleration, this gives us that the magnitude for our centripetal acceleration, right, when we're at 5 centimeters away from the axis of rotation, that centripetal acceleration is going to be equal to R2 divided by R1 multiplied by the magnitude of the centripetal acceleration when we're at 3 centimeters away from the center of rotation. So all we got to do is plug some stuff in. So the centripetal acceleration, when we're 5 centimeters away from the center of our disk, it's going to be equal to R2 which is 0.05 meters, divided by r1, which is 0.03 meters, times the magnitude for our centripetal acceleration when we're only 3 centimeters away from the center. But the problem tells us that that is 120 meters per second squared. And so multiplying this out, this gives us that the centripetal acceleration of a point that is 5 centimeters away from the center of this spinning CD-ROM is 200 meters per second squared. So that's the answer to this first problem. So let's now move on to example number 2. Again, this is from the uniform circular motion chapter. So example number 2. Example 2 talks about a satellite. So the problem says that a satellite is in a circular orbit around an unknown planet. Around an unknown planet. So the satellite has a speed. The satellite has a speed of 1.7 times 10 to the 4 meters per second. And the radius of the orbit is 5.25 times 10 to the 6 meters. So the problem goes on to say that a second satellite also has a circular orbit around the same planet. So a second satellite also has a circular orbit around the same planet. So has a circular orbit around this same planet. So the orbit of this second satellite, the orbit of this second satellite has a radius of 8.6 times 10 to the 6 meters. 6 times 10 to the 6 meters. So the problem is asking, what is the orbital speed of the second satellite? So what is the orbital speed of the second satellite? Very good. So in this problem, we need some force to act as our centripetal force. Now, in this case, it's going to be the force of gravity between this unknown planet and the satellites. So when we're looking at, one particular object, we have that the centripetal force is the force of gravity acting on that object. But on the left, the centripetal force is just the mass of the object times the centripetal acceleration of the object. Right? Then on the right, it's just the gravitational, it's going to be the gravitational force between our object and our unknown planet. So I'm going to call MP the mass of this unknown planet. Little m is going to be the mass of our satellite, whichever one we're looking at. It's going to be divided by r squared. So what we can do we can actually solve this for v. So notice that here the masses are the same, so those get canceled out. And if I multiply both sides by r, we get that v squared is equal to g times the mass of the planet divided by r. And then if we want to find v, right, the speed of the satellite as it orbits, right, all we have to do is take the square root from both sides. So we get that v is going to be the square root of g times the mass of the planet divided by r. Right. Here I just want to point out that g, right, is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Right. So here's what we can do. Let's say that, you know, the second satellite, I guess let's call it the first satellite, right? Its speed is going to be given by this thing that we found here. So g stays the same, the mass of the planet stays the same, but we're at some radius r1, which according to the problem is 5.25 times 10 to the 6 meters. So this is our r1, right? And then v2 is the speed of our second satellite. So again, that's going to be equal to the square root of g times the mass of the planet divided by r2. So notice that this problem doesn't tell us the mass of the planet. So we need to find some way of getting rid of that and still being able to find our answer. So what we can do, kind of like what we did in the last problem, we can divide v2 by v1. So the speed of the second satellite divided by the speed of the first satellite is going to be equal to, so up top we have v2, so it's going to be the square root of g times the mass of the planet divided by r2 and the square root. And in the denominator we have the same thing, but now with r1. Right. So when we do this, the square root of g cancels out, excuse me, that one. Square root of g cancels out. The mass of the planet cancels out. And this boils down to square root of r1 divided by r2. Right? Because up top stays the same. And then we have to basically flip the bottom. So r1 goes on top, r2 goes on the bottom. So now we have v2 over v1 is equal to this stuff. And we can solve for v2, right, the speed of the second satellite, by multiplying both sides by v1, the speed of the first satellite. Right, so this is v2 is equal to r1 over r2, right, times v1. But we know what the speed of the first satellite is. So the speed of the first satellite, v1, is 1.7 times 10 to the 4 meters. And we also know what the orbit, like the radius of the orbit for the second satellite is. Right? That's 8.6 times 10 to the 6. So plugging all this in, this is going to be equal to r1, which is 5.25 times 10 to the 6 meters, divided by r2, which is 8.6 times 10 to the 6 meters, and all of that is under square root. Then we're multiplying all that by v1, which the problem tells us is 1.7 times 10 to the 4 meters per second. Right? So if you punch this into a calculator, we get that the speed of the second satellite is 1.33 times 10 to the 4 meters per second. So that's the answer to the second problem. All right, so now let's move on to our third example. So this is example 3. And so example 3 comes from the chapters on work and energy. So example 3 says that a 55 kilogram box, is being pushed a distance, of 7 meters. 7 meters across the floor by a force. Across the floor by a force. You know, this force is going to be called P for the pushing force, not to be confused with the linear momentum. So pushed across the floor by a force P, whose magnitude is 150 newtons. Whose magnitude is 150 newtons. Right. So the force P is parallel to the displacement of the box. So the force P is parallel to the displacement of the box. So when we go to calculate like the work done here, that means that our theta for P and our displacement is going to be 0 degrees. That's all that means. So the problem goes on to say that the coefficient of kinetic friction, is 0.25. So let me actually just write that coefficient of kinetic friction, 0.25. Easier to write in symbols than it is in words. Problem goes on to say that we want to determine the work done on the box by each of the 4 forces that act on the box. So determine the work done on the box by each of the 4 forces that act on the box. So by each of the 4 forces that act on the box. All right, pretty standard work problem. So let's draw a picture. We have ground. We've got a box, which looks like this. I'm going to draw in a coordinate system where x goes to the right, and it's parallel to the ground. So this is x. I'm going to say that y is the vertical direction, like so. Positive y points up. And now I'm going to draw in the forces. So our first force is going to be the normal force of the ground pushing up. Ground pushing up on our box. Then we have this pushing force P. It's pushing it to the right. Then we have the weight of our box pulling down. Just write mg, I guess. And then finally, if the box is being displaced to the right, the force of friction is going to try and oppose that. So the force of friction points to the left. I'm going to call that Fk. Okay. So first of all, let's begin by noting that we don't want this box accelerating in the y direction. We don't want it rising up, and we don't want it sinking into the ground. So when we look at Newton's second law of all the forces acting in the y direction, it's going to be equal to the mass of the box times the net acceleration of the box in the y direction, but we want that to be 0. So the sum of the forces on the box in the y direction are going to be the normal force pointing up, and then the weight pointing down. So we have the normal force pointing up. So it's positive, right? Because it's pointing the positive y direction. And we have the weight mg pointing in the negative y direction. So it gets a minus sign. And it's equal to 0. Right? And this just tells us that the magnitude for our normal force is going to be equal to the magnitude of the weight mg. But our weight mg, right, we can calculate because we know the mass of the box. So g, the mass of the box is 55 kilograms. Forget the box. G is 9.8 meters per second squared. So it's kind of implied that we're on Earth. So, you know, whenever we're in doubt about what planet we're on, just assume it's Earth. So this is going to be a normal force of 539 newtons. Right, so that's our normal force. So next up, we can actually calculate the magnitude for our kinetic frictional force, right? Because that's just equal to our coefficient of kinetic friction times the magnitude for our normal force. But we know both of these things, right? Because the problem tells us that our coefficient of kinetic friction, 0.25, and our normal force we just found to be 539 newtons, right? So multiplying those two things together, we get a kinetic frictional force magnitude of 134.75 newtons. 134.75 newtons. Okay. So we also know that finally the magnitude of our displacement is 7 meters. So let's calculate the work done by all of these. So the work done by this pushing force P is equal to the magnitude of the force times the magnitude of our displacement times cosine of the angle in between them. Right? But the magnitude of the pushing force is 150 newtons. Our displacement is 7 meters. And as I mentioned before, since our pushing force and our displacement are both in the same direction, the angle between them is going to be 0, and cosine of 0 is going to be 1. So the work done by the pushing force P is 1,050 joules of work. That's one of our answers. So then the work done by our kinetic frictional force is just going to be the magnitude for our kinetic frictional force times our displacement times cosine of the angle in between them. So in this case, our magnitude is 134.75 newtons. That's what we found up here. 134.75 newtons. We know that our displacement has a magnitude of 7 meters. And the angle between our displacement, which is in the positive x direction, and our kinetic frictional force, which is in the negative x direction, points this way, that angle is going to be 90 degrees plus an additional 90 degrees. So in this case, this is going to be 180 degrees. So cosine of 180 degrees, right, this thing right here, is equal to -1. So the work done by our kinetic frictional force in moving the box forward, the work done by this kinetic frictional force is minus 943.25 joules. Okay. So the work is negative because the box is moving to the right and our kinetic frictional force is pointing in the exact opposite direction. Right. So last but not least, the next two are going to be easy because we're looking at the work done by our normal force and our weight in taking the box and moving it 7 meters directly to the right. So Right, our expression for work is the work done by a force is equal to its magnitude multiplied by the magnitude of our displacement times cosine of the angle between our force and our displacement vector. Now, in this case, our normal force is perpendicular to our displacement, right? This angle here for our normal force is 90 degrees. And since cosine of 90 degrees is 0, that means that the work done by the normal force is also 0. So does 0 joules of work in this particular case. And additionally, we know that the angle between, our displacement vector, which points to the right, and our weight is either 270 degrees for going counterclockwise around. Right, this whole angle here is 270, or we can do minus 90, whichever one fits our fancy. But both cosine 270 degrees and cosine negative 90 degrees, both of those are also 0. And because of that, it turns out that in this problem, the weight, the work done by the weight of our box and moving it, 7 meters to the right, that is also 0 joules of work. And because of that, we've now found the work done by each of the 4 forces in our problem. So with that, we've done the problem. Found out everything the problem is asking us to do. Let's go into example 4. So example 4, again from the work and energy chapter. So example 4 says that a rescue helicopter lifts a 79 kilogram person, straight up by means of a cable. Straight up by means of a cable. So if you predicted this is going to be a tension problem, you're correct. So the problem goes on to say that the person has an upward acceleration. The person has an upward acceleration of 0.7 meters per second squared. Meters per second squared. Oh, there's no period there. And is lifted from rest through a distance of 11 meters. So, and is lifted from rest through a distance of 11 meters. Through a distance of 11 meters. So what is the tension in the cable? So I guess part A is asking, what is the tension in the cable? Part B is asking, how much work is done by the tension in the cable? So work done by tension. And part C is asking the person's weight is person's weight. And part D is asking us to use the work energy theorem to find the final speed of the person. Use the work energy theorem find the final speed of the person. All right, so we have some work to do. So to begin with, let's write down what we know. So the mass of the person, 79 kilograms, just like that. And the person's net acceleration in the y direction is 0.7 meters per second squared. Right? So the person is initially lifted from rest. So the initial velocity of the person is 0 meters per second. And the final speed of the person is something the problem wants us to ask that, but the displacement D, is 11 meters upwards. Very good. Let me just move some of this stuff over. Right. We can draw a free body diagram of this person. I'm going to write this person as, being a block as usual, as per usual. Right, so now we're going to draw in our coordinate system. In this case, this is a one-dimensional problem, so we don't have to worry about stuff in the x direction, but we're going to say that things moving vertically are moving in the y direction. So positive y is directly up. And there's two forces acting on this person. So there's the tension force, T, pulling the person up. And then there's going to be the weight of the person pulling the person down. So what we can do, so we know that when we look at Newton's second law in the y direction, that's equal to the sum of the forces in the y direction, but that's equal to the mass of the person times the person's net acceleration. So we only have two forces in this problem, right? The tension pulling up and the weight pulling down. So this becomes the tension T pulling up minus the person's weight pulling them down. And this is going to be equal to the person's mass times their net acceleration in the y direction. Right. Now, if we add this to both sides, if we add the weight to both sides, we get that the tension in this cable is equal to the mass times the net acceleration of the person plus the mass times the acceleration due to gravity. Right, that's equal to our tension. But we can factor the person's mass out. So the person's mass. And what's left is the acceleration in the y direction plus the acceleration due to gravity g. And so we can solve for part A, right, by just plugging in some values. So the mass of the person, 79 kilograms. Then we have that multiplied by the person's net acceleration in the y direction, but that's 0.7 meters per second squared, plus the magnitude for the acceleration due to gravity. So it's going to be 9.8 meters per second squared. And so this is going to give us a tension in this cable of 829.5 newtons. All right, so that's part A. So part B is asking for the work done by the tension. So for part B, the work done by the tension is equal to the magnitude of the tension multiplied by the magnitude of the displacement multiplied by cosine of the angle between our displacement and our tension force. But both our tension and our displacement are both in the same direction, right? They're both pointing upwards. Person's being lifted by this rope, tension is pointing upwards. So this angle here is going to be 0. So the work done by the tension in lifting this person up is going to be equal to the magnitude of the tension, which we just found to be 829.5 newtons, multiplied by the magnitude for our displacement. That's 11 meters. Multiplied by cosine 0 degrees. But cosine of 0 degrees is just 1. So plugging all this in, we get that the work done by the tension force is simply equal to 9,124.5 joules. So 9,124.5 joules. So that's part B. Okay, so I think I goofed. So part C is not actually asking for the person's weight. It's asking for what is the work done by the person's weight. So we're not just multiplying m by g. We're actually trying to find the work done by, the force of gravity when we're lifting this person up. So that's going to be part C. So the work done by this person's weight in lifting them up is equal to the magnitude of his weight, which is mg, right, multiplied by the magnitude for our displacement times cosine of the angle between our displacement and the direction that the weight is pointing in. Well, our displacement is pointing directly upwards, right, because the person is rising upwards, but the weight is pointing directly downwards. So there's an angle of 180 degrees, right, no matter which way you slice it, there's an angle of 180 degrees between our displacement and the weight. It's 180 degrees. And so now we just got to plug some stuff in. So the mass is 79 kilograms. G is 9.8 meters per second squared. D is the magnitude for our displacement. That's going to be 11 meters. And cosine of 180 degrees is just -1. So when you put all this stuff together, you get the work done by this person's weight is minus 8,516.2 joules. 0.2 joules of work. So this is going to be part C. And so finally, we have part D, which is asking us to use the work energy theorem to find the final speed of the person. So we need to use the work energy theorem to find the final speed of the person. So a good place to start is by just writing down the work energy theorem. So the work energy theorem says that the net work done on an object is equal to the change in that object's kinetic energy. Right, so it's going to be the final kinetic energy minus the initial kinetic energy for our object. Right, and rewriting this, we have the net work done. Now I'm just going to fill in the right side because we know how to calculate the kinetic energy of an object. That's 1/2 times the mass of the object times the magnitude of the velocity of that object squared. Right, so for our final kinetic energy, it looks like that. And we have minus 1/2 times the mass of our object times the magnitude for our initial velocity squared. And that gives us our initial kinetic energy. So the net work done is going to be equal to the change in our kinetic energy. Right. But we know that initially our person starts from rest. So the magnitude of our initial velocity vector is 0. So this whole term is going to be 0 because B naught is 0. Right? And the problem is asking us to find the final velocity of this person. So it's going to be V sub F. And on the left-hand side, we have the net work done in lifting this person 11 meters, right? So the net work done is just going to be equal to the work done by the tension force plus the work done by the weight, right? Since these are the only two forces in the problem. If there were additional forces acting on this person, we would need to include them here, but since there's only two, we only have to worry about these two. But we solve for these in the previous parts, right? So the work done by the tension is this right here, right? So that's 9,124.5 joules plus the work done by the force of gravity. So the work done by the force of gravity is minus 8,516.2 joules. Just like that. So the net work done in moving this person, a distance of 11 meters upwards is going to be 608.3 joules worth of net work. Right. So in this case, that's going to be the left-hand side. And for the right-hand side, we just need to solve for our final velocity. So really what we're dealing with is we have the net work done is equal to 1/2 times the mass of our person times final velocity magnitude of our person squared. And so what I'm going to do, I'm going to multiply both sides by 2 to get rid of this 1/2. Then I'm going to divide both sides by m to get that our final velocity for this person squared. It's going to be equal to 2 times the net work done divided by the mass of the person. And then last but not least, if I take the square root of both sides, we're going to get the final velocity that we're looking for. Right. So this is going to be our final velocity is equal to 2 times the net work done divided by the mass of the person, all under the square root. So now we're just got to plug some stuff in. Right, so this is the square root of 2 times the net work, which we calculated to be 608.3 joules worth of work. And then the mass of the person, 79 kilograms. Right, and all this is under the square root. And so when we punch that into a calculator, the final velocity of this person after we've lifted them up a distance of 11 meters is going to be 3.92 meters per second. And so that's the final answer for this problem. All right, so let's move on to example 5. So example 5. Right, says that a ball of mass 10 kilograms is dropped from a height of 100 meters. So what is the final velocity? Right, there's the magnitude. So what's the final velocity of the ball just before it hits the ground? Okay, so the way that we're going to solve this one is by using conservation of energy. So let me just draw a quick picture. So we have, our ground, and then our ball starts from somewhere up here, right? Here's our ball. And so this distance between, where the ball starts and ground, this is a distance of 100 meters. Oh, and something else that I need to include here is that the initial velocity of the ball, something that I should have added in the problem, but I didn't. So the initial velocity of the ball, let's say that it's 0 meters per second. right? So it's starting from rest. So this is our ball, right? It wants to figure out the velocity of the ball just as it's hitting the ground. So we're going to use the conservation of energy in order to solve this, right? Because in this problem, this ball is only acting under the force of gravity, being, pulling it downwards. And so since gravity is a conservative force, right, that means that the energy, until the ball hits the ground, the energy of this ball is going to be conserved. So I'm going to say that our initial energy of our system is when our ball is, up here, and then our final energy is right when our ball, just before our ball hits the ground. So we're going to use conservation of energy to solve this problem. So the conservation of energy says that the total energy that we start with is going to be equal to the total energy that we end with, right? They're both the same. So let's look at this. Our total energy to begin with is going to be our initial kinetic energy for our ball plus our initial gravitational potential energy for our ball. So this is going to be our initial kinetic energy, which is 1/2 mv naught squared. And our gravitational potential energy is just mgh naught. Right? But since we're starting with an initial velocity of 0, right, we're dropping this ball from rest. That means that this term is gone. Because again, v naught is 0. And h naught here is our initial height, but our initial height is just 100 meters. So in this case, our initial energy is just going to be mgh, h naught. So that's going to be the mass of the ball, which was 10 kilograms. Kilograms. Just like that, times g, which is 9.8 meters per second squared, times our initial height of 100 meters. Right. Clean that up a little bit. So this is going to be equal to, right, our initial energy for our system is 9,800 joules of energy. And so now let's look at the final energy of our system. All right, so the final total energy is going to be our final kinetic energy plus our final potential energy, final gravitational potential energy. All right, so that's 1/2 times our final velocity squared, 1/2 mv final squared plus mg hf. But I'm going to say that hf, right, our final height is when we hit the ground, which I'm calling 0. So because of that, our gravitational potential energy in this case is going to be 0, because hf is 0. Right? So our final kinetic energy is entirely kinetic energy. So it's just 1/2 mv final squared, right? And so keep in mind, the problem is asking us, what is the final velocity magnitude of the ball, right, just before it hits the ground? So we're looking for this. But because we can use the conservation of energy here, and we know that our initial energy is equal to our final energy, our initial energy is 9,800 joules, and our final energy is just 1/2 times the mass of the ball, just 10 kilograms, right, times our final velocity for this ball just as it hits the ground, squared. So if I multiply both sides by 2 and divide both sides by 10, we get a final velocity of our ball squared. That's going to be equal to, right, 1,000 960 meters squared per second squared. And finally, if we take the square root of both sides, we get that final velocity of this ball just before it hits the ground is going to be about 44.3 meters per second. So this is us solving the problem using conservation of energy. So the next problem we're going to look at is example 6. Just zoom in a little bit. So example 6. So example 6 comes from the impulse and momentum chapter that we just covered. So this says that a 0.5 kilogram ball, 0.5 kilogram ball is dropped from rest, at a point 1.2 meters above the floor. At a point 1.2 meters above the floor. Goes on to say that the ball rebounds straight upwards. The ball rebounds, it bounces up, so it rebounds straight upward, to a height of 7 meters. To a height of 7 meters. I do not know how that's physically possible, but whatever. So what are the magnitude and direction? So what are the magnitude and direction of the impulse of the net force applied to the ball during the collision with the floor? So applied to the ball during the collision with the floor. During the collision with the floor. All right. So we know that our impulse, J, is equal to the change in momentum of our object, right? So that's going to be our final momentum minus our initial momentum, where our final momentum is the mass of our object times our final velocity, and our initial momentum is the mass of our object times our initial velocity. So to begin with, we have to find the velocity with which the ball hits the ground, right? So we know that our ball starts from here, goes like this, it's falling straight down, and the initial height of our ball, right, is 1.2 meters. 1.2 meters, just like that. So since the initial velocity of our ball is 0 meters per second, right, because our ball is dropped from rest, it's an important bit, right? If we use that the final velocity of our ball in the y direction squared minus the initial velocity of our ball in the y direction squared, That's going to be equal to 2 times our acceleration, which in this case is just the acceleration due to gravity, times our displacement, delta y. So the velocity that our ball hits the ground with, actually even taking a step back, our initial velocity is 0, right, because that's 0. So that term's gone. So our final velocity in the y direction, right, just as it hits the ground, it's going to be equal to the square root of 2 times our acceleration due to gravity. But our acceleration due to gravity is going to be minus 9.8 meters per second squared. Delta y is going to be minus 1.2 meters, right? Where the minus sign is because our displacement is downwards. So this is going to give us the magnitude for our velocity, just as it hits the ground, of, this magnitude is 4.85 meters per second. But because we know that our velocity is both, or is a vector, it's got both a magnitude and direction. So I'm going to call the velocity just as this thing hits the ground, it's going to be minus 4.85 meters per second, right? Where the minus sign indicates that the thing is actually falling downwards. Oh, I see. Okay, so it's not 7 meters, it's 0.7 meters. That's a typo. Okay, this makes a lot more sense. Okay, so now we need to find the velocity of the ball after it hits the floor and bounces back up. So the next picture that we're looking at, we've got a ball, right? It bounces up off the floor. And now it's ascending upwards and reaches, its max height of 0.7 meters. Right. So this height is now 0.7 meters. And now our ball is, traveling upwards. So when the ball is being, bounced back from the ground after hitting it, this first part, right, ball comes down, hits the ground, and now the ball has changed its direction. So now the ball is going upwards like this. I'm going to call this velocity after rebounding off the ground, v2. And we know that at max height, which in this case is 0.7 meters, this velocity is going to be 0 up here, right? So now we're going to do the same thing that we did in the first part. We know that our final velocity in the y direction squared minus our initial velocity in the y direction squared is going to be equal to 2 times acceleration times our displacement in the y direction. In this case, since our final height, or our final velocity in the y direction is going to be 0, right, because this is 0 as defined by max height. This is going to be equal to minus our initial velocity, but our initial velocity is what we're calling v2. So it's going to be minus v2 squared. It's going to be equal to 2 times our acceleration due to gravity, times our displacement in the y direction. So we have that magnitude for our rebounding velocity, right? That magnitude is going to be equal to the square root of minus 2 times g, which is minus 9.8 meters per second squared, times our displacement, which is, right, positive 0.7 meters going upwards. And all this under the square root. So this minus sign is going to cancel with this minus sign. And we get the magnitude for v2, right, our rebounding velocity. That's going to be 3.7 meters per second. And in fact, in vector form, right, this is, since it's moving upwards, it's basically the same thing, right, where the fact that this is a positive number indicates that it's moving upwards. So now we know the initial velocity of this thing just as it hits the ground. So in this first picture, we solved for v1. So this is our initial velocity. And then our final velocity is v2. So going back to our impulse problem, right? So the impulse is equal to the mass times our final velocity minus our mass times our initial velocity, right? Our final momentum minus our initial momentum. And we can factor the m out. So it's going to be our final velocity minus our initial velocity. But our mass, so the mass of this ball is 0.5 kilograms. And our final velocity is going to be our velocity v2, which in vector form is just that. So it's 3.7 meters per second, minus our initial velocity, which in vector form we found to be that. So minus 4.85. Minus 4.85 meters per second. Right. This minus sign cancels that minus sign. So our impulse, right, and all said and done, our impulse is going to be 4.275 kilograms times meters per second. Right. So the magnitude of J in this case is just 4.275 kilograms meters per second. And the direction is indicated by the fact that in vector form, this is a positive number, right? So this tells us that this impulse is directed upwards. And so that's the end of our problem. So that's example 6. Now for our last problem of the day, let's look at example 7. So example 7 says that a 5 kilogram ball, moving to the right, moving to the right at a velocity of 2 meters per second. So at a velocity of 2 meters per second on a frictionless table. Frictionless table. So whenever you see like that our problem doesn't involve friction, you can probably assume conservation of energy. And in this case, it looks like we're going to be colliding two balls. So this is probably going to be an elastic collision. In fact, it's actually going to ask us to solve both situations. So this is saying that this ball moving to the right at a velocity of 2 meters per second on a frictionless table collides head-on, with a stationary, so it's not moving, 7.5 kilogram ball. 7.5 kilogram ball. So the problem wants us to find the final velocities. So find the final velocities of the balls if the collision is, so if the collision is A, elastic, and B, completely inelastic. Completely inelastic. All right, so let's just draw a little picture to get our bearings. So to start with, we have ball 1. These are not going to be drawn on a scale. Ball 2. So ball 1 has a mass of 5 kilograms. Ball 2 has a mass of 7.5 kilograms. Right. And initially, ball 1 is moving to the right. So the initial velocity of ball 1 has a velocity of 2 meters per second, where the fact that it's positive 2 meters per second indicates it's moving to the right. And our second ball has an initial velocity of 0, right? It's initially not moving. And so we are tasked with finding the final velocity of these balls, right? If this isn't for part A, an elastic collision, for part B, a completely inelastic collision. So let's start by looking at part A. So for part A, we're dealing with an elastic collision. So the way that we're going to solve this is by using the fact that both our momentum is conserved as well as our kinetic energy. Right. So let's do that. So our initial momentum is going to be the momentum of ball 1 plus the momentum of ball 2. Right, but the initial velocity of this second ball is 0, so that term's gone. So it's just the mass of the first ball times the initial velocity of the first ball. Right, so all the momentum in our problem initially comes from this first moving ball. This is going to be 5 kilograms times its velocity of 2 meters per second. And so we get an initial an initial momentum of 10 kilograms times meters per second for our system. So afterwards, right, we have mass of our first ball times the final velocity of our first ball plus the mass of the second ball times the final velocity of our second ball. So it's just going to be 5 kilograms times the final velocity of ball 1, which we don't know, plus the mass of ball 2 times the final velocity of ball 2, which we also don't know. But what we do know is that our initial velocity, our initial momentum is equal to our final momentum. So we know that 5 times our final velocity for ball 1 plus 7.5 times our final velocity for ball 2. We know that this is equal to 10 meters per second. Right, where I've divided through by 1 kilogram to get rid of units of kilograms here, here, and here. And so this is going to be equation 1. Equation 1. And next up, we need to make use of the fact that the kinetic energy is conserved. Right? So our initial kinetic energy is going to be 1/2 m1 v1 squared plus 1/2 m2 times the initial velocity of the second ball squared. But again, the second ball initially isn't moving. So this whole first term, which depends on the second ball's initial velocity, is 0. So this is just equal to 1/2 times the mass of the first ball, which is 5 kilograms, times the initial velocity of the first ball squared. So in this case, our initial kinetic energy is 1/2 times 5, which is 2.5 times 2 squared, which is 4. So this is going to be 10 joules. So that's our initial kinetic energy. But our final kinetic energy is the kinetic energy of both balls after the collision. So that's 1/2 m v final 1 squared plus 1/2 m2 v final 2 squared, right? Now at this point, we can't really do much with that. So 1/2 times m1, right? If I multiply, I can't do that yet, so never mind. So this is going to be, 1/2 times m1, which is 5 kilograms, times the first ball's final velocity squared, plus 1/2 times m2, which is 7.5 kilograms, times the second ball's final velocity squared, right? And that's going to be our final kinetic energy. And we know, because of conservation of kinetic energy in this point, right, because this is an elastic collision, so by definition, our initial kinetic energy is equal to our final kinetic energy. We have, and I'm going to multiply both our initial and our final kinetic energies by 2 to get rid of these pesky 1/2s. So this is going to be 5 times the final velocity of our first ball squared plus 7.5 times the final velocity of our second ball squared. And it's going to be equal to 20 joules. All right, so I got this by setting this, our initial kinetic energy, equal to our final kinetic energy, and then I literally just multiplied both sides by 2 to get rid of these 1/2s. Because I didn't want to deal with them. So this right here is going to be our equation 2. And so now what we're going to do, we're going to solve equation 1. So we're going to solve equation 1 for, the final velocity of our first ball. So in this case, from 1, we see that the final velocity of our first ball is going to be equal to 10 meters per second minus 7.5 times the final velocity of our second ball, all divided by 5. So again, this is just solving equation 1 for this final velocity for the first ball. This is going to be equal to 2 meters per second minus 1.5 times the final velocity of our second ball. And so now we can take this and we can plug this right into equation 2 whenever we see the final velocity for our first ball. So let's do that. So looking at equation 2, we have 5, well, I guess, so looking at 2 now, equation 2, right? So we have 5 times our initial velocity, or excuse me, our final velocity for ball 1, but that's just equal to this stuff that we found. Right, so that's 2 meters per second minus 1.5 times the final velocity of our second ball. So we're going to square that. And then we know we have the rest, which is times 7.5 times the final velocity of our second ball squared. It's equal to 20 joules. I guess in this case, right, we've divided by kilograms, so this is going to be, well, some weird unit of meters squared per second squared, right? And we're going to, multiply all this stuff out, and then I'm going to move this over to the left-hand side, so we get our, this into a quadratic equation sort of form. So this is going to give us 18.75 times the final velocity for our second ball squared minus 30 times the final velocity for our second ball. And it turns out that's going to be equal to 0. Because this 20 gets canceled out by some of the stuff that falls out of this. And so we just have to solve this for the final velocity for our second ball, right? So if I add this to both sides, on one side we get 18.75 times the final velocity of our second ball squared. It's going to be equal to 30 times final velocity of our second ball. Right? So there's actually two solutions that solve this equation right here. Right? If I make the final velocity of the second ball, right? If I make that 0 meters per second, then if you plug 0 in here and 0 in here, then it's true that the left-hand side of this equation will equal 0. But that's not valid, because if we look at our little diagram here, so it doesn't make sense if our first ball comes in and hits the second ball. It doesn't make sense if the second ball doesn't move, right? It's not nailed in place by anything. There's no friction in our problem, so it doesn't make sense that the final velocity of this thing is 0. So it's either that, or you'll notice that if I divide this equation right here, right? If I divide it by the final velocity, then this thing here gets canceled by one of these, right? And then I can divide both sides by 18.75. So then we get a final velocity for the second ball, which is 30 divided by 18.75 meters per second. So this gives us 1.6 meters per second. And that's actually pretty valid. So we have the final velocity for our second ball is 1.6 meters per second. That's one of them. And now that we know what the final velocity of our second ball is, we can plug that in to here to find the final velocity for our first ball. So final velocity for our first ball is equal to 2 meters per second minus 1.5 times the final velocity of the second ball, which is just 1.6 meters per second. And when we do this, we get a final velocity for the first ball of minus 0.4 meters per second. Right, where this minus sign indicates that the first ball came in. Right, this first ball came in, hit the second ball. The second ball continued this way at a velocity of 1.6 meters per second. But then this first ball bounced backwards and is now traveling backwards at minus 0.4 meters per second squared. Or excuse me, meters per second. So there's our answer. Now for part B, we need to look at this from a completely inelastic collision point of view. So part B, we're looking at this from a completely inelastic point of view, right, which just means that our initial momentum is equal to our final momentum, right? The momentum's conserved, but the kinetic energy is not conserved. But a completely inelastic collision means that, the two balls will collide, and then they'll stick together and they'll move at the same final velocity. So the final velocity of the first ball is going to be equal to the final velocity of the second ball, which is going to be equal to some final velocity. So we do like we did before, right? We see that the initial momentum of our system is just the momentum of our first ball plus the momentum of our second ball initially. But our second ball was initially not moving. So that's gone. So this is just, 5 kilograms. The mass of our first ball times the initial velocity of our first ball, which is 2 meters per second. All right, so our initial velocity, or excuse me, our initial momentum, P naught, is still 10 kilograms times meters per second. And our final momentum is just M1 V1 final plus M2 V2 final. But since this is a completely inelastic collision, the final velocities are going to be the same. All right, so this is just equal to mass of the first ball plus the mass of the second ball times the final velocity of both of the balls together. So in this case, right, the mass of the first ball is 5 kilograms, mass of the second ball is 7.5 kilograms. This is going to be equal to our final velocity. All right, so our final momentum is just 12.5 kilograms times the final velocity of the two balls together. So we have that our initial momentum is equal to our final momentum. So on one side we have 10 kilograms times meters per second. And then on the other side we have 12.5 kilograms times our final velocity of both balls, right? So we get, when we divide both sides by 12.5 kilograms, we get a final velocity of 10 divided by 12.5, or 0.8 meters per second. So there's the answer, part B. And with that, we've completed our problem. In fact, we've completed the entire lecture.